Spend a little bit of time with you all on the concept of concave up and concave down. I felt that this was one of the topics that we briefly touched on and that we should revisit just to make sure that the concept is pretty solid. You can always refer to your textbooks, but hopefully having the video will be nice as well. So the first one that we're going to take a look at, we're going to investigate concave up. Okay, so in class we had said that anything that was concave up, it looked like a cup or kind of like a wine glass in a sense, because it will catch anything if it falls into it. So one of the ways that we can kind of describe anything that is concave up is if you use the idea of tangent lines. So an example of a tangent line would be what is about to appear in green. And this is a line that abuts or is right next to the function. So notice that since our function in this case is curved, if we put a straight line next to it, it will not touch everything perfectly. It's going to only touch maybe one or a few points. But if you notice, if we draw a series of these lines, so if I continue to kind of go from left to right and kind of use this straight line and travel from left to right, what we'll notice is that the lines, as I keep going, are going to become less negative, or in other words, we could also say more positive. They mean the same thing, we're just describing it in two different ways. Now, the slope will eventually, if we get to the local minima, the slope will eventually become 0. So the slope is equal to 0 here. But if we continue along this path, so if we, once we get past that minima and we start adding more of these tangent lines as we continue to travel, notice that these tangent lines are becoming steeper, and each of these are actually becoming more and more positive. So since they are increasing in steepness, going from left to right, so in other words they're pointing upwards, we again are seeing a situation where the slopes are becoming less negative, or in other words, more positive. So for concave up, what we can basically say is that the rate of change, or in other words, when we say rate of change, we can also say slope, because that does mean the same thing. The rate of change will become more positive on either side of the local minima. Okay, so again, notice that on the left-hand side, so looking at those tangent lines that we have noted in green, as I continue to move from left to right, the slope is becoming less negative. So if it is becoming less negative, it's approaching positive values. Once it gets past the local minima where the tangent line would be equal to 0, because that's the tangent line there would be a horizontal line, and we start moving to further right along this curve, our slopes are positive, and notice that they are increasing in their positive value. Since the steeper a positive slope is, the larger that slope becomes. So we can use the same idea when we talk about concave down. Again, if we use, if we follow along this function from left to right, if I were to start drawing tangent lines, so there's one, notice that it looks like the lines are starting to fall. So they're starting to become more and more horizontal. Sorry about that. The lines started to erase themselves. Okay. So it looks like they're falling, or they're becoming more horizontal. So if this is the case, we can say that in this case, since we are starting off with slopes that are positive, they are becoming less positive. Or in other words, if they are becoming less positive, they're moving closer to the negative values. So in other words, they are becoming more negative. And then again, once we reach, in this case, our local maxima, the tangent line is going to have a slope that's equal to 0. And now as we move to the right side of this function and we start drawing tangent lines, we're going to notice, okay, this line that we have in red, it has a negative slope because if you look at it from left to right, it is decreasing. And then as I add the next one in pink, it dips further, and then the next one further continues to dip. So as you can tell, since again I am getting closer and closer to a vertical line, we can actually say here that again the slope is becoming less positive because it's becoming actually more negative. So that being said, for concave down, we can basically take the same description that we have on the left-hand side here in purple and just switch out a couple words. So the rate of change, or in other words, our slope, becomes more negative on either side of the local maxima. Okay. So one last point to make. If we are looking at, say, a function that looks something like this, and I do apologize that this is not going to be on a coordinate plane. But basically, now what I've done is I've kind of molded or blended two functions together. One of them is concave down, and one of them is concave up. And what you basically want to know when you are identifying something that is concave up and concave down is where it actually begins to twist and change direction. So recall that, say, since we're just guesstimating here, this point in orange, this is called the point of inflection. So what the point of inflection is, again, it's basically the turning point where something shifts from going concave down to concave up or vice versa. So in this case, we would note that what I'm going to kind of highlight in pink is going to be where it will be concave down. We would note when this is on a coordinate plane that we would use interval notation to indicate from what x values to what x values our function is going concave down. And then what I will highlight in, I don't know, this lighter green-blue color, this is where it is concave up. Because again, so we would note that from the point of inflection and on. So I hope that this brief tutorial or this brief catch-up was helpful. If you have any other questions, please let me know, and I'd be happy to help.